Hello, everybody. Welcome to the first maths workshop for the term. Let's get straight into it. So we'll start with a general overview of competitive mathematics and CPM SOC, and then we'll go into the specific competition that most people at UNSW participate in, which is Simon-Mirai. And we'll explain a little bit about what the format for those questions and those exams is like. And then we'll go into more abstract principles of problem solving and competitive mathematics. And we'll finish off with introducing proof by contradiction and going through a few questions there. So the Simon-Mirai competition is in mid-October, and it's 4 questions of paper and 2 different papers. Usually it's held on a Saturday, and you go in, or last year you joined a Zoom call, and you do 4 questions in the space of 3 hours, and they're marked out of 7. Usually you get either 0 marks, 1 mark, 6 marks, or 7 marks, depending on how well you do. So reasons to participate in competitive mathematics would be social participation. You want to meet smart people who like solving problems. You want to solve problems yourself and challenge your brain. And you want to look good on a resume or in a job interview. Those are the main attractions of competitive mathematics. But I'm sure if you talk to people on the Discord, they'll have all sorts of other reasons. So the Simon-Mirai competition, the questions are usually in each of the 2 papers, increasing in difficulty. And the last question has historically been an open problem. That is, it's unsolved by anybody ever. Usually it's pretty niche, but it's always explained in a way where you can understand the question, but the method of solution is not clear. And that's true of all the questions. That's basically the distinguishing feature of competitive mathematics, as opposed to mathematics you do in uni, in high school. So the problems in the competition, your solutions to them need to be proof-based in the sense that they present some argument, as opposed to just stating a solution. Usually the questions will be phrased in terms of find some number or prove some property, but you always need to rigorously justify each step you're taking. To solve problems, so you read the solutions after having looked at the problems and thought about them for a little bit. It's very satisfying when you find a solution. Generally, it's some ingenious but clearly understandable trick that lets you reframe the problem and see the answer very clearly. So these are a few of the subject areas that are covered in the competition, and often they'll be combined in particular questions, but usually it's helpful before you begin a question to just have a think about which parts of mathematics is this pulling together and which tools do I think would be relevant from those parts of mathematics, from what I and from what I practice. So the difference between competitive math problems and exercise problems that you do with that, or a maple quiz or some homework assignment, they're less rote. They're less about applying techniques, more about combining the techniques. Obviously, you need to be able to apply them, do the computations, calculations, but most of the difficulty of the problems comes from the way you put those tricks together. And we'll see that in a few of the questions later on. So if you want to learn that kind of thinking, which is orthogonal to just computation, the problem-solving mindset, obviously you need to practice, like with anything, but you should practice strategically. As in, you should do things like, if you've done a question, you should go back and after you've forgotten the answer, you should go back to the question and see if you can solve it again, especially if you didn't get it the first time. And sometimes you'll remember parts of the solution that you read, but the fact that you remember them means that your brain has digested that technique. And if you understand the general argument of any solution you read, that's a win. Like, you don't need to solve every question. Nobody's going to get full marks. It's very, very rare. But you do want to be able to understand the solutions you're presented with after the fact. And you want to be able to digest those and pick out the general problem-solving principles that you can apply to other questions. So some general strategies you'll see mentioned in problem-solving literature around mathematics is things like writing down your thoughts clearly, reframing the problem in a way that's a better expression of the fundamental question that's being asked, reframing the setup, or maybe taking bits of information out, or adding bits of information in that make the problem easier, and then seeing if maybe you don't need those in there. Other things like working backwards from what a solution would look like. Maybe ask yourself, what would the step immediately before the solution be? What information would I need to know? And if you ask yourself questions like that, you can set smaller tactical goals to work towards. It also helps, as soon as you see a question, without some abstract setup, you should probably give the variables values and see what actually happens. Sometimes it's computationally difficult, like if it's asking about some combination of 100 different variables. You might want to make the problem a simpler problem than you're presented with, and then try plugging in numbers and seeing what happens. And usually that will lead you to some theories or hypotheses about the problem setup. And that will lead you to asking the right questions to set those smaller tactical goals, which you can then work towards. You also need, obviously, to understand the particular techniques of proofs and solutions to achieve those smaller tactical goals. But a lot of these will be, some of these will be general, but a lot of them will be tailored to particular subject areas. These ones are fairly generic, but things like generating functions, you'll see those more in sequences, series, those kind of questions. But usually some of the harder questions, you might see some of these techniques being applied in solutions where you wouldn't necessarily expect them based on the content of the question. So you should probably keep an open mind about which techniques you're going to use to solve the problem, because you don't know until you've seen all the possible solutions. So there's a few books that our society has recommended if you want to go deeper into problem solving, but these workshops should be fairly comprehensive if you just want a general overview of the techniques and the strategies and the mindset. And then if you want to get good at competitive mathematics, you can read these books, but I think more effective would be just do some problems. And books like Putnam and Beyond are just problems, basically. a little bit of explanation of theory in there, but it's mostly about problems, going back and doing the problems he's presented. Things like that are the main way to get good at something like this. So the Putnam archive, the Putnam is basically Simon Murray in the USA and Canada. It's a very big deal with top unis like MIT, Harvard, that kind of thing. And it's very old competition. So if you ever want to find questions on particular topics, you can just Google Putnam questions, and it'll usually come up with stuff. But the Putnam archive is just a website that lists all those questions with solutions. You can also use YouTube videos if you want to have a more passive way of taking in math content. There's a few channels out there like Michael Penn, 3 Blue 1 Brown, Black Pen, Red Pen. If you just Google math on YouTube, you should be able to come up with something, especially if it's on a particular topic. Wikipedia is very formal, generally. You'll see things like, I think the entry for a vector in Wikipedia says a vector is an element of a vector space, which maybe isn't so helpful if you're trying to just understand the basics of vectors. So Wikipedia is generally more formal, but if you really want to go deep into a particular mathematical subject, Wikipedia is going to tell you absolutely everything about that subject that they think is relevant. There's also our Discord, which you should definitely join. And I might give you like 30 seconds right now just to write that down, or enter that link into your browser and the Discord server, because if you're struggling with understanding a particular solution, it can really help either to have it explained to you by somebody else, you can then ask questions to, or to try to explain it to somebody else and see the bits that you're confused about, and then go back and think about those more, research those more, and eliminate your confusion. Cool. These slides will also be available after the presentation, by the way, on the website, if you want to have a look at them. So let's get into the actual content for today, which is proof by contradiction. So a proof is basically some series of statements where each statement is either taken as a part of the setup of the problem, or else it follows from parts of the setup in the sense that it's logically implied by them. So a proof by contradiction is a very simple, basic form of an argument. It really, if you understand what implication is, and you think about this for a little bit, it becomes very obvious, I think, why this is true. If you have some statement like, Robert is a cat, and you know that cats have fur, usually. If Robert doesn't have fur, Robert is not a cat. That's basically proof by contradiction. All the things you've had to assume are that cats have fur and Robert does not have fur. Those are the two assumptions, and if you combine those, you get the proof by contradiction in the most general form. We'll get into some particular examples. So the classic one is proving that there are infinitely many primes. We want to suppose that there are not infinitely many primes to begin with. And then we'll just enumerate those for convenience. We'll say these are the finitely many primes that there are. If we multiply all those together and add 1, we get some other number. And we want to prove that this other number is not one of those primes, but is also a prime, because that would contradict our original assumption. Q is larger than any of the primes we've listed, so it can't be prime, and it's bigger than 1, and it's a whole number, so it has to be a composite number. Q is not divisible by any of the primes listed, since division by any of them leaves a remainder of 1. See that if you look at the equation that defines Q, if you think about dividing it by any one of those primes, you'll have a remainder of 1, which means it's not divisible by any of them. If it's a composite number, it has to be divisible by some prime, since it's larger than 1. So we're saying that it's divisible by a prime, but it's also not divisible by any prime, which is contradiction, which means the thing we assumed that is not always true. We assumed that there are finitely many primes. We didn't know that, but now we know that it's false. Because if we assume that and we apply things we do know, then we reach a contradiction. A contradiction is anywhere where you have a statement A and also not A. So Robert is a cat and Robert is not a cat is a contradiction. If you reach a contradiction, you know that whatever you assumed has to be false in some way. Another example would be, here we're trying to prove that that product on the screen is an even number. We're also given that n is an odd number. So the first step in any proof by contradiction is, of course, assume the opposite of what we want to prove. So we suppose, for argument, that A is odd. Each one of those numbers is also going to be an odd number, since if one of them were even, then the product would be even, since they're all whole numbers. If those subtractions are all odd, well, the first subtraction we have A1 minus 1. Minus 1 is an odd number. We're adding it to A1 and getting an odd number. It means A1 has to be even. A2 minus 2, if that's going to be odd, we know that A2 has to be odd. And so if we count up the different A numbers, we can split it into two different piles. One of them is an even pile and one of them is an odd pile. If we count the number of numbers in each pile, since n is an odd number, if you look at the A2, A4, A6 up to AN minus 1 pile, there's going to be n minus 1 on two numbers in there. Since n minus 1 is an even number, and we're counting up by twos n minus 1 times, the first pile is going to have n plus 1 divided by two numbers for the same reason. So from this, we can conclude that since A1 to AN are rearrangements of the numbers 1 through n, if A1 through AN has n minus 1 on two even numbers and n plus 1 on two odd numbers, that means that the numbers 1 through n also have to have n minus 2 even numbers, n plus 1 odd numbers. If that's, then we know that A has to be even because one through n does not contain n plus 1 and two even numbers and n minus 1 and two odd numbers. 1 through n contains n minus 1 and two even numbers and n plus 1 and two odd numbers, just by looking at the sequence. So we can see that A1 through AN has some property that 1 through N does not have. And since we're saying they're the same set of numbers, that's a contradiction, which means that A has to be even because what we supposed that A was odd led to a contradiction. Yasir, do you want to take this question?
Oh, yes, question 2, yeah.
Great.
All right. So question 2 is prove square root 2 plus square root 3 plus square root 5 is an irrational number. So many of you may have seen the question of proving square root 2 is irrational, and that uses a famous proof by contradiction method where you can square both sides and use divisibility by 2 to eventually get a contradiction. So for this question, it's just an extension of the square root 2 problem. So all we can do is, again, use proof by contradiction. So the first step we can do is to assume that square root 2 plus square root 3 plus square root 5 is equal to R, where R is rational. So I think there's a typo there. It should be a 5 instead of a 4. All right, so that's the first step. Okay, so what we can do is square both sides. So the purpose of squaring both sides is to try to remove or undo the square roots. And the good thing about undoing square roots is the number of square roots gets less and less, so it becomes easy to get our contradiction. So when we square both sides, first we have to rearrange. So you can move the root 5 over to the right hand side, and you have square root 2 plus square root 3 on the left hand side and R minus square root 5 on the right hand side. And if you square both sides, you get 5 plus 2 root 6 is equal to R squared plus 5 minus 2 R square root of 5. Okay, so now wait, hang on. Okay, so then we get that square root of 6 plus R times the square root of 5 has to be rational by, again, rearrangement. It's because if you move the 2R square root of 5 to the left hand side and you cancel out the 5s, you'll get square root 6 plus R square root 5 is equal to R squared over 2. So yeah, square root 6 plus R square root of 5 must be rational. And if you square both sides again, you'll get 6 plus 5R squared plus 2R square root of 30 must be rational. And if you subtract 6 plus 5R squared, you'll still get a rational number. And if you divide by 2R, you'll get square root of 30 has to be rational. Yes, now we see square root of 30 has to be rational. So the next step is we can let square root of 30 equal P over Q, where P over Q is a fraction in lowest form. So GCD of P and Q is 1, and Q is not equal to 0. Okay, so when you square both sides again, you will get P squared is equal to 30 times Q squared. Okay, so now we can investigate some prime factors on both sides. So what we see is 30 is even, so P squared has to be even, and this forces P to be even. So since P is even, when you square P, you'll get 2 factors of 2, so P squared has to be divisible by 4. Now if you write Q squared as P squared divided by 30, since P squared is divisible by 4, but 30, it only has 1 factor of 2. That means that P squared over 30 will still be divisible by 2. And so it means Q squared is divisible by 2. So that forces Q to be divisible by 2. So Q has to be even. So this is where we get our contradiction, because we got the result of P being even and Q being even, but this contradicts the assumption that GCD of P and Q has to be 1. That's where we get our contradiction. So since our contradiction came from the first step of assuming the original number is rational. That's why we get square root 2 plus square root 3 plus square root 5 is irrational.
Great. Yeah, this question has a lot of algebra, so it's probably a little difficult to follow. Do you want to maybe run through the broad argument again, Yasiru? Just slowly.
Okay. So we have square root 2 plus square root 3 plus square root 5. So it's a sum of 3 square roots, so it's not that easy to work with. All you can do is, if you keep on squaring both sides and rearranging, what we can get is we can undo lots of the square roots so they become whole numbers, and whole numbers are a lot easier to work with because if you add a whole number to a rational number, it still stays rational. So you want to make as many whole numbers as you can by squaring. So if you look at step 2, you can see that the number of square roots has gone down from 3 to 2, because in step 1 there was 3 square root stuff, and in step 2 it's gone down to 2. And again, if we rearrange and square, if we look at step 3, we see that now there's only 1 square root, which is square root of 30. So the square roots keep on going down, which makes the problem a lot easier. And so now the convenient thing is we can now subtract whole numbers, or we can subtract rational numbers off, and the result will still be rational by our assumption. And so we finally get square root of 30 must be rational by our assumption. And now you can finish your problem off using the same method as proving square root of 2 is irrational by analyzing prime factors. So that's where we assume square root 30 is P over Q, and our assumption is GCD P of Q is 1. So that's just writing the fraction in lowest terms. And then step 5, 6, and 7 are proving that P and Q must both be even, and that's where we get our final contradiction. So that's why the original number is irrational.
Great, thank you. Yeah, this question is some of these questions you kind of need to write them out and follow them through to understand where you're going. I said before that most of the questions in a maths competition will be fairly aesthetically pleasing. Obviously, that's subjective. But I think you'll generally find that understanding the big picture argument is more important than following through all the little bits of algebra here. So I guess the key steps here would be square and rearrange to get rid of the square roots, like Yasser said, and look at the prime factors and the greatest common denominators. So that's using some number theoretic techniques there. And then if we do that, we can apply the same techniques that we know from a general irrationality proof, like root 2, to reach our final contradiction. So I think just digesting that general broad argument is much more important here than following the particular algebra. So don't worry if you're too confused about that. Yeah, Sarah, do you want to briefly explain this question, and then we might give some people some time to think about it?
Oh wait, this was not the question I was assigned to, I'm pretty sure, but
yeah. Also, we have a question in chat. So how do you deduce that q squared has a factor of 4 from q squared equals p squared on 30?
Yes, Sarah, do you want to take that one?
Oh yeah, so how to deduce that q squared as a factor of 4 from q squared equals p squared over 30. Oh yeah, so he says he gets it, but yeah, I can explain it again. So since p was even, when you square p, what happens is p has one factor of 2, and when you square it, it has two factors of 2, so it is divisible by 4. And 30, it only has one factor of 2, so when you divide p squared by 30, you'll still have one factor of 2 remaining. And that means that q squared must be even. And the only way that can happen is when q is also even. So that's why q squared is divisible by 4. I think it may have been written in the wrong order. It should say yeah, it should say q squared is a factor of 2. So q is yeah, it should say q squared is a factor of 2, so q is even.
Yeah.
Let me
But
change that. I mean, it works, but I'll change that in the slides for when we upload them as well.
Yeah, it's a correct statement, but yeah, we haven't.
A little unclear, yeah.
It's unclear, yeah.
Cool.
Great. And feel free to jump in with any questions like that if you have them, and we'll try to take them if we spot them. If we don't spot them, then we'll spot them eventually, and we'll jump back and explain that bit if you're confused.
Okay, so this question here is a little bit different to the previous ones. Do we want to allow a little bit of time for people to kind of think about it and come up with maybe their own solutions, or?
I think maybe just explain the general setup.
Okay, so we've got some polynomial, which hopefully you're familiar with from high school or whatever, and it has even degree and a positive leading coefficient. So if you're familiar with kind of the shape of polynomials, we know that it's going to be, I guess, kind of like a smiley face, right? Now, we're trying to show that if p of x minus the second derivative of p at x is greater than 0, then p of x is at greater than or equal to 0, right? So in a sense, we have p of x is defined so that it has even degree and a positive leading coefficient. Those are things that we can always take as assumptions, right? The second part is an implication. If we know that p of x minus p, the second derivative is always greater than or equal to 0, then p of x is greater than or equal to 0. If we want to approach this as a contradictory statement, then we would try and start with if it's possible that p of x is not greater than 0 for all real x. So in order to do that, we're going to assume that p of x is, okay, first of all, there is a note. So because this comes from the even degree note, because it's of even degree, we know that as x approaches plus or minus infinity, so towards the end of the number line, we end up getting that p of x approaches infinity. So this means that the polynomial, because it's finite at some point, we know that the polynomial has a minimum value, and we know that minimum value has to be finite, because obviously the minimum can't appear towards kind of the infinite ends. If you had a odd degree polynomial, then one of the ends would be going to negative infinity, so there would be no minimum. And if you had a negative leading coefficient, then both of the ends would be going to negative infinity, so there would be no minimum. So this is just one part that comes in further on, which you may notice starts to help, and it's probably not something you would begin with. So if you were writing this out, this is something that helps us later on in the proof. But if you're writing this out, I would generally start with a contradiction, and then as the contradiction comes along, I would notice kind of properties about this graph that may help us further on. So the next step here, or basically the first in any proof, would be to suppose that instead we know that there is some part of this polynomial which is less than 0. So we know that p of x, or we're supposing that p of x is less than 0 for some real x, and we want to derive a contradiction from here. So do we want to give them a little bit of time to try and go further from here, or should we just explain it?
Well, I think in broad terms, if you're doing a proof by contradiction, we might just jump back to the explanation of proof by contradiction quickly. So jump back here. We've supposed we now want to show some information. That's the next general step here, and from there we want to get to some false statement, which we know is false by the setup of the problem. I'll give you 2 minutes to think about that, let's say. So I hope you've had a bit of a think about that problem. I think in general, when you're reading solutions to problems, especially if you got them wrong, it's very easy sometimes to just look at the words and not absorb them into your brain. So something that really helps, in my opinion, is partway through the solution that you're reading and try to think about what other pathways you could take from there to get to the final answer.
Alrighty. So this is where the minimum remark comes in. So in particular, we know that we're trying to prove that p of x minus p double prime of x is less than 0. Now, the only information we can kind of glean from this is it's even degree, positive leading coefficient, and that p of x is less than 0 at some point. That's the assumptions we're starting with for our contradiction proof. P of x being less than 0 doesn't really help us other than knowing that the p of x term there is less than 0. We need to find some way to learn something about p double prime, so the second derivative of our polynomial. However, what we do know is because it's even degree with a positive leading coefficient, if any part of it drops below the x-axis, so is negative, then the minimum must also be negative. We can't have a minimum that's positive then, right? And what the minimum gives us is some way to relate that single point, whatever the minimum is, with the second derivative. Because as you may know, the second derivative at a minimum is always positive. It's always concave up, so the second derivative is positive at any minima, as long as it's continuous, and polynomials are. So there is a minimum, and let's say a is the minimum, and we know that the second derivative is greater than or equal to 0 at that minimum. So because it's greater than or equal to 0, its negative is less than or equal to 0, and adding something that is at most 0 to something that's less than 0 gives you something less than 0. So adding both of them together, we get that p minus its second derivative at a is less than 0, which contradicts our original assumption that we have a polynomial with even degree, positive leading coefficient, such that p of x minus p double prime of x is greater than 0, and our contradictory assumption of p of x is less than 0. So adding all of that together, we end up taking our original assumption, which was not part of the question, and saying that must be false, so it must be greater than or equal to 0 for every real number. Cool.
Thanks, Ethan. And yeah, I think it's very important to distinguish in a proof between things that you're assuming for the sake of argument and things that are in the setup of the question. You don't want to get those confused. because otherwise you might end up with circular reasoning or other kinds of things. If you're assuming something, you need to be very clear that you're assuming that for the sake of argument.
So one way I would say if you're doing a contradiction proof, one good way to start it is, rather than saying suppose that P of X is less than 0, telegraph to the marker or whoever's reading your solution that you're aiming for a contradiction. So suppose towards contradiction that P of X is less than 0, then you're very clearly stating that that assumption is made so that you will come to a contradiction at some point. You know it's wrong, and you're assuming it on top of the question that was already given you.
Wazy, did you have a question? Sorry.
I think that was from earlier.
Yeah, that was the previous question. Yeah.
Cool. Great.
All right, so question 3. Question 3 states that there are 9 planar surfaces. So you just think of it as different figures that we should draw on a plane, and you can think of them as regions of a plane, and each of these regions has area of 1. And now if you combine all the regions together, the total area is 5. And the question states that prove that the overlap of some of these 2 surfaces has an area greater than or equal to 1/9. So the first thing I would do for a question like this is to draw a diagram, so you can draw these planar surfaces and try to visualize the situation and try to see what information you're given. So what you're given is each surface has an area of 1 and the total area is equal to 5. And now the question says prove that the area of some 2 of these surfaces has an area at least has an overlap of at least 1/9. So the annoying part of this question is you don't know which 2 surfaces in advance. You don't know which 2 surfaces will have an overlap of at least 1/9. So usually in maths, there's 2 types of proofs. You can either construct something, you can show a concrete example of something that works. And there's also existence proofs where you can prove that something exists, although you don't exactly know explicitly what the construction is, but you can still show that it exists. So this question is an example of showing that something exists, even though you don't know concretely which 2 surfaces will overlap at 1/9. So for questions like these where you can't construct which two surfaces has an overlap of at least 1/9, proof by contradiction is a good method, because you can do lots of assumptions. You can do it the other way around, where you can assume that all the surfaces has an overlap of at most less than 1/9. So this makes things easier, because proving that something exists is not that easy, but if you assume that lots of stuff fail, then it makes the question easier. So for proof by contradiction, we will assume that no 2 surfaces intersect at an area of at least 1/9. Yes, that's the first step. So suppose that the overlap of every 2 surfaces is less than 1/9. Okay, so now we can number the surfaces or label them as S1, S2 up to S9. So we can do it arbitrarily, so it's not important which surface is labeled as which.
I think this is a good thing to point out. Usually when you're beginning a question, picking good notation for all the objects involved is a very generically applicable principle that lets you reason more clearly about the problem and get your thoughts down on paper so you don't forget them or get muddled up.
Yeah, so yeah, we'll number the surfaces S1, S2 up to S9. Okay, so what we can do is we can draw a diagram and add surfaces one at a time and see what happens. and use our assumption that the overlap of any two surfaces is less than 1/9, and we can see what happens. So since the question is given that the total area is equal to 5, we can try to see what happens to the total area when we add one surface at a time. Let's take the surface S1, which has area 1, and then add S2. So now we can investigate the situation. So you can think of it as, you can visualize it as a Venn diagram almost. So you could have a circle and another circle that intersects the first circle. So even though these are arbitrary plane surfaces, when you're drawing a diagram, you can pretend that the surfaces are as simple as possible, such as a circle, just to make things easier. And by our assumption, we know that the union of S1 and S2, oh wait, before that, we know that the intersection of the first two surfaces, S1 and S2, it must have an area of less than 1/9. So what it means is, if we take surface S1 and then we add S2 on top of it, or we add S2, what we can see is that if we want to find the total area, we can add the area of S1 and add the area of S2, but then we have to subtract some area lost to the intersection, because we can't count the intersection twice. So we have to subtract the intersected area. So if we add the area of S1 and S2, that's 1 + 1 = 2. And if we subtract the intersection of S1 and S2, we know that the S1 and S2 intersection is less than 1/9 by assumption, which means that the amount of area we subtract is less than 1/9. So another way of saying it is S1 and S2 combined have an area greater than 2 - 1/9, which is the same as 1 + 8/9. Okay, so now we can do a similar process. So step 3, we considered the first two surfaces, and now we can add another surface. So now we have the first 3 surfaces. So we have S1 and S2 in step 3, and if we add the third surface, we can again investigate what happens. So when you add S3, you're adding. So what you can do is, you can add the area of S1 and S2 combined, and then add the area of S3, but finally you have to subtract the area that S3 intersects with from S1 and S2. So again, you do a similar process where you can add the areas together and subtract the intersection. That gives you the total area of S1, S2, and S3 combined. So from earlier, S1 and S2 combined have an area greater than 1 + 8/9. So now S3, the amount it intersects with S1 is less than 1/9, and the area S3 intersects with S2 is also less than 1/9. So the amount of new area added when you add S3 will be at least will be greater than 1 - 1/9 - 1/9. So if you do the calculations, you get the total area is more than 1 + 8/9 + 7/9. So the area must be at least 1 + 8/9 + 7/9 when you consider the first three shapes combined.
I might get people just to pause here and have a think about what they think we're going to contradict about the original problem setup here. So you can see that we're building up this collection of planar surfaces, and you can see that the area seems to be increasing. So what do you think the final conclusion is going to be that contradicts our setup here? I'll give you maybe a couple seconds to think about that one, and then we'll keep going.
Yes, I think Anonymous has a good idea the total area is not equal to 5. That's a promising idea, because that's an important piece of information we're given. And if we can contradict a given piece of information, then we know that we've reached a contradiction.
Maybe guess now whether you think it's going to be bigger than 5 or less than 5. It should be reasonably easy given what we've established so far and where we're going. Cool.
Okay, so you can continue the pattern from step 3 and 4. So you can keep on adding a new figure one at a time and seeing how much new area is contributed by each new figure. So if we add S4, for example, the total intersection with S1, S2, and S3 is going to be at most 3 times 1/9. So the new area added by S4 is more than 6/9. And if you do S5 similarly, the new area it adds is more than 5/9, and so on. So if you continue the pattern and consider the new area added by each new figure, you'll get that the total combined area is more than 1 plus 8/9 plus 7/9 plus ... plus 1, 1/9. And if you add these all together, you get the total area is greater than 5. So from our original assumption that every intersection of two surfaces has area less than 1/9, we've reached the conclusion that the combined area of all 9 figures is greater than 5. And this is very problematic because if we see the original statement, the total area has to equal 5. It can't be more than 5. So that's very problematic. So we have reached a contradiction. So our original assumption that every overlap was less than 1/9, that was a false assumption, which means some two surfaces must have an overlap of at least 1/9. And another thing is, again, we don't know which two surfaces have an overlap of at least 1/9. So even though we have this proof, if someone drew some random nine surfaces which satisfy all the conditions, this proof doesn't help figure out which two surfaces have a combined area of 1/9, but you can still guarantee that some two surfaces have a combined area of at least 1/9. So this is an example of a non-constructive proof. So non-constructive proof is where you show that something exists, but you actually don't know what it is, but you just know it exists. Another example would be proving infinitely many primes, for example, because when we did that proof of multiplying all the previous primes together and adding 1 and getting a new prime number, we don't know what that new prime number is, but we just know it exists out there. That's another example of a non-constructive proof.
Yassir, somebody's asking, first of all, why is this not just the pigeonhole principle? And second of all, why would you apply proof by contradiction in particular to this question?
All right, so pigeonhole principle. All right, so proof by pigeonhole principle, for those who don't know, states that if you have pigeons and you put them in pigeonholes, so for example, if you put 15 or 13 pigeons in 5 pigeonholes, then you must have at least 3 pigeons in some pigeonhole. So that's a very useful technique, and you can generalize it. So it means that if you have more than mn pigeons and you put it in n n pigeonholes, then you must have at least m pigeons in one pigeonhole. So for this question in particular, okay, I'm not aware of a proof that uses the pigeonhole principle, but you could give it a shot. And for motivation for proof by contradiction, so one motivation is, and it's really again, the thing about non-constructive proofs I said about, it's hard to actually do a direct proof where you can show which two surfaces have a combined area at least 1/9. So since it's pretty hard to do a direct proof, we can aim for an indirect proof where you can assume by assume for contradiction that all pairs of two surfaces have a combined area or intersected area less than 1/9. So that will be a motivation for using contradiction. So it's just hard to attack this problem directly.
Yeah, I think the thing about contradiction is it's a very logical way of approaching it. Logical in the sense that it deals with implication and what's called contraposition. So contraposition is if P implies Q, then Q being false implies that P is false. So because it's so abstractly logical, it's pretty well suited to situations where you don't want to get into the details and construct something. Obviously, you still have to do computations to reach that logical implication that you use to make the final inference that the original supposition is false. But you don't necessarily have to construct something when you're doing a proof by contradiction. So it's good for dealing with messy situations like this one, where you don't know a whole lot about the surfaces.
I will
in
say
terms of
though,
the pigeonhole principle,
there is a
Yeah.
pigeonhole principle solution to this, which you may, so when we're coming up with the overlap of some two surfaces has an area greater, it's basically we're saying there exists some overlap. So you can phrase that in the sense that the overlap are the pigeonholes, and we're trying to get excess area within those pigeonholes. So yes, there is a way to do it that way. But I feel like, at least personally, while I'm looking at this, I would probably start off with contradiction. It's a kind of simpler way, I suppose, in my eyes. If I look at this, I would go, I can see a non-constructive proof, and I know that everything here is very easy to negate so that I can use them as extra assumptions.
Yeah, but it's definitely good, even when you're solving a problem in a competition setting, to keep an open mind about what kind of strategies might be best. And definitely when you're practicing, you should try to solve a problem in more than one different way. And you should share solutions with other people if that's appropriate, because that lets you read other people's solutions, let you see how you should write your solution to not be confusing, but also what different techniques and ways of thinking about things you can apply. Another more general principle here, you'll notice that we only just got an area greater than 5. Like the numbers here are very precise, in the sense that they add up to exactly 5. And in general, the numbers in competition questions will usually be picked to just give you the right answer. So looking at what those numbers are and what the arithmetical relationships between them are sometimes lets you kind of metagame what the solution might be, or what good solution strategies, which solution strategies are going to be the best.
Cool. Okay. So I will, before we go into this, I will say that this question is a little bit difficult. If you're not familiar with induction, some of the reasoning behind it can be a little bit hand wavy as well. So we're given an interval, and we're asked to show that it can't be partitioned into two disjoint sets, A and B, such that B equals A plus A for some real number A. So basically what we're saying here is we're taking 0, like all of the numbers between 0 and 1 inclusive of 0 and 1, And if we split it into two parts that are disjoint, so they don't share numbers, we want to try and find a way to do that so that one of them is exactly the other one, but you take every number in it and just add some number to it, a in this case. So for example, you could take maybe the interval 0 to 0.5. Then if you add 0.5 to that, you would get the interval 0.5 to 1. You've taken every number within there, you've added 0.5 to it. So this one here relies on a little bit of set theory, which is something you'll see crop up quite a bit. But there's also kind of, if you look at this, you can kind of see a little bit of symmetry. Not in like the classical geometric sense here, although in a sense there kind of is. If you look at, you've got a split between A and B, and B is A plus some real number, A. Now, because it's real, it can be positive or negative. And dealing with positive or negative numbers, or which one, if we want to use A or B specifically for a certain purpose, can be a little bit difficult. So we can swap the role of A and B. If A is negative, then instead of thinking of it as B is A plus that extra number, we can think of it as A is B minus that extra number, which makes it positive. So in a sense, we're looking at this and trying to simplify it to something that we can work with a little bit kind of easier, right? So the first step here would be to maybe look around, explore, and see that there is a way that we can force the role of certain parts of this. We've got two sets, we can force one of them to be in a particular form, which may help us later on. So instead, we can assume that A is greater than 0. Now, to start this off, we need to try and think about what we're trying to kind of accomplish here. So we're trying to show that it cannot be partitioned into two sets, which is basically a blanket statement of saying it is not true that it can be partitioned. So another way to write that is, rather than, if we're showing that it cannot be partitioned, we can do the opposite. We can assume that it can be partitioned. And if we show that, if we assume it can be partitioned in this way, then we have a contradiction. Then we know that that assumption there, even though it is effectively the entire question, that assumption there must be false. And we can negate it back to the original question. So in this case, we're going to try and suppose that we can partition the interval 0, 1 into two disjoint sets such that B is A plus some real number, right? So, oh, I didn't actually write that down. So the next step doesn't actually include, okay, so that's the supposition. The supposition is that we can split it into two sets satisfying these properties, right? Now, we know that if we think about kind of the endpoints, right? So 0 in particular, if we think about 0, it needs to be inside the set A. If it's in B, because A is positive, then that means we have something in A that when we add a positive number to it gives us 0, which means it's negative. But also we know that A and B partition the interval 0, 1. So everything in there is positive, so that can't be true. So 0 needs to be inside A. And something similar can be said for all of the other numbers between 0 and A. So the interval 0 to A must be inside A, right? Yeah, so we've kind of got the first section of our number line must be included within A. And now we can think about, well, if we add A to all of those numbers, they need to be in B, because B is defined as take everything in A and add A to it, right? So the next part is we know that A up to 2A must be inside B. Click. There we are, yeah. So A to 2A must be inside B. And we can kind of continue this pattern using induction. Now, being able to come up with seeing this as induction kind of just comes from seeing a pattern and seeing if you can roll with it. If you know that the first A numbers, or the first like interval of size A needs to be inside A, and the next interval of size A needs to be in B, then you can kind of see, well, maybe it needs to flip back and forth. And you can explore that opportunity. You can sit down, write out some numbers, and try and prove that maybe 2A to 3A needs to be inside A. So exploration is kind of key to this kind of question. You write down maybe a number line, figure out what needs to be where, and then go, okay, well, can this number be anywhere? No, it can't. It needs to be shifted around. It needs to be inside this set, right? So this next part is a induction argument. In particular, if we have 2ka to 2k plus 1a, I'm just waiting for the slide to appear. There we go. So 2ka and 2k plus 1. So k here is an integer. 2ka and 2k plus 1a is in A. Then we know that the next kind of set needs to be in B, because if we add a to every number there, we're going to go from 2ka to 2ka plus a, which is 2k plus 1a, and then it continues going up until 2k plus 1a. Add a to that, you get 2k plus 2a. That should be an a, not a b. I'll fix that. So we have one kind of section with a many elements, or not a many, it's not numbers, but an interval of size a. And the next interval of size a must then be in B, right? But if we had some number inside the next one, then if we subtract a, it needs to be an a, right? So if we take everything from 2k plus 2a, again, typo, to 2k plus 3a, and we subtract a from it, then it ends up being inside that interval earlier, 2k plus 1a, 2k plus 2a. So if it's inside that interval, it would need to be in B, so it couldn't be in A. So this is kind of like a sub-contradiction proof, which is why I said this is a little bit complicated. We're assuming that we can split things up. So we've got a contradiction proof to begin with. Then in order to kind of establish a pattern, you would be using induction here. So induction is used to establish a pattern that we've identified. Now, finding that pattern, you don't need to know induction, right? Finding that pattern, you can fiddle around with numbers and you'll eventually find it. But proving that that pattern holds, you will need to be using induction or some other kind of proof method. Induction's the big one for patterns and that kind of thing. So we're using induction here, but within it, the inductive step itself is a contradiction proof. Rather than saying we take a number, we add a to it, oh, it must be part of the other set. We can't exactly do that. We don't have a way to take elements from B and say that they must be in a later part of A. So instead, we have to try and flip the argument. We have a way to say if you take something in A and add a to it, you get something in B. And we can flip it to say that if you have something in B and you subtract a from it, then you have something in A. So if the next part is B, then subtracting it will give you A, right? So you can kind of think of it from two different ways. You're saying after every section of A, we have a section of B, and every section of B comes after a section of A. So the next section of B needs to have an A before it, and we start to alternate. So we go B to A to B to A. So the induction argument here is kind of a formal way of explaining this out. We have a section of A, then a section of B. Then we must have a section of A, because if it's a section of B, then backwards we must have a section of A, and obviously we can't have A and B are intersecting, right? We know that A and B are a partition, so they must be disjoint. We can't have elements in both A and B at the same time. So this is the kind of complicated part. It's something that I would recommend kind of sitting down, or if you have a question about it, specifically asking, but like sitting down and trying to get through this and understand exactly why this induction argument works. Effectively, we're saying that we have a section of A, we have a section of B, and then after that, we have a section of A, followed by a section of B, followed by a section of A, so on and so forth. So it alternates between sections of A and B throughout the whole thing. Now, we can actually, now that we have the whole structure of A, effectively, and B, I guess, we know that A must be made up of sets of the form 2ka, 2k plus 1a, and B of sets of the form 2k plus 1a, 2k plus 2a, right? So we're alternating back and forth between them. We're splitting up the number line into sections of A and sections of B. And we've found this by assuming that there is a partition. So we've assumed there is a partition, and we've shown that the partition then must be in a very specific format. It can't be anything else. It must specifically be sections one after the other, right? So we've narrowed down the problem to, if there is a solution, it must satisfy these constraints. And now we're trying to see if maybe those constraints don't give us what we want. Maybe those constraints contradict something, so that we can get a contradiction to the supposition that we actually have a way to split these sets up. So the last bit is to notice that A and B together must be 0 to 1, right? It's a partition of 0 to 1. So adding them together should give us the whole 0 to 1 set. So one of them must contain 1. But because A and B are both kind of sections, right? They're sections of size A from NA to N plus 1A for some natural number N. And this interval must contain 1 because it's an open interval. So this is the part of this where we kind of look at the structure of it, right? We've got 1 must be part of this interval, and it's an open interval on the right. Oh, I'm afraid this question just went overhead. What is the question even trying to say? Okay, so the B equals A plus A is saying that B is the set that you get if you take the entire set A and add A to everything inside of it. So if the set were 0 and 2, right, then B would be A and 2 plus A. But of course, these are infinite sets. So we can't really say like, take A and add it to the first, second, and third number. There's not necessarily any order of them. It's just all of them, right? Yep. So it's kind of like saying if you got A, so A is a part of 0, 1. B is then if you got that set and just shifted it over a little bit. So what we've shown here is that the only way for that to be possible is if A is kind of sections that are cut up, and then shifting it over fills in the other sections. And then we know that 1 is contained in it because it's a partition of the whole 0, 1 set. And because 1 is in it, then it must be part of an open interval on the right. So the interval it's contained in must be open on the right. But we know that then 1 can't be the maximum within that. There must be a number larger than 1 within that set. And since we've assumed that A and B are a partition of 0, 1, that interval can't contain anything larger than 1. If it contains something larger than 1, then it's not a partition of 0, 1, it's a partition of 0 to something larger, right? And that's where we derive our contradiction from. So our contradiction comes from, if 1 is contained in one of these, then we must contain a number larger than 1, so we don't have a partition, right? It no longer partitions 0, 1. And that's the final statement. So we cannot partition in this way because that gives us our contradiction. So effectively, we've shown that if we have a partition, breaking it up, it must be broken up in a specific way. And breaking it up in that specific way gives us a number larger than 1. So it can't actually be a partition. We have a contradiction. So our original supposition that we can split it up into a partition is wrong. The reals are uncountable. So it doesn't have to do with reals being uncountable in particular. It's just you can't really think. I guess you kind of think of like it being you take 2 sets and you just add A to each element. It's just there's infinitely many. You can't order them. That kind of thing. It's to do with being able to shift things over. So, okay. So yeah, when we're shifting things over, so it's because the intervals are of a particular form. So because A contains 0, B must contain A, like the little a, right? Which means that the interval 0a must be open on the right-hand side. Now, if we have a bunch of intervals that are open on the right-hand side and add them all together, then the total interval must be open on the right-hand side as well. But 0, 1 is closed on the right-hand side, so we're going to get an issue at that border, is where we're kind of going with this. So NA N1 plus A containing an element larger than 1 just comes from the fact that if 1 is in if 1 is in that interval, because it's open on the right-hand side, it can't be equal to N plus 1A. So N plus 1A needs to be larger than 1. I think a formal definition of an interval might be a little bit nice. So if you have, say, the interval, I'll type it in chat. So if you have the interval AB, so A is closed on one side and B is open on the other, that's saying anything inside there satisfies this. A is less than or equal to X is strictly less than B. Yep. So if 1 is that X, then there must be something between 1 and B, which is also part of that interval. Yeah, so there's no maximum interval, basically. Yeah. No maximum element. There's no maximum element in that interval. So if 1 is in there, it can't be the maximum. There must be something larger than that.
Ethan, do you think you could maybe give some geometric intuition for this proof?
Am I able to draw?
You could try annotating.
Am I allowed to annotate it? Oh, I
Possibly.
can. Oh, beautiful. All right, yeah. So geometric intuition behind this might be a little bit easier.
Yeah, I can't see your annotations.
Can you move to the next slide real quick? Just so I have extra space to draw.
We'll go back here.
Yeah, okay, cool. So can you see that?
Yeah.
Cool. I'll quickly change the color to something a little bit easy to see. Maybe red. I'll go red. So what we're doing is we know that we have some number line. I'm really bad at straight lines. So this is 0 here, and this is 1 here. And we know that 0 must be part of one of them. Because we've assumed A is positive, we know that 0 must be part of A, right? So this section here, between 0 and A, is all within the set A, right? Now, B is A if you shift it over a little bit. So the next kind of section here to 2A must be contained within B. And then this kind of pattern continues. And inductively, what we're looking at here is if we have some element in the next section, say this one here, if it were in B, then if we subtracted A from it, we'd end up in here in A. So if this were B, then subtracting A from it should give us something inside the A set. But it doesn't. It gives us something inside the B set. So it can't be inside B. Instead, we must have that element inside A. Right? So the next section must be inside A. And our inductive argument is just rigorously proving that this pattern holds. So showing that it's true for the first one. So that was our original bit where we showed that 0 to A is part of it. And then our inductive step is saying if this section here is in A, then this section here must also be in A. And if that's so, then the next section must also be in A, and the next section must also be in A, right? So it's sections being part of it. You can kind of, if you know that A follows that pattern, then you know that B follows that pattern as well, because all we're doing is shifting this A along, and then this A gets shifted over to here. There's another A over here, which gets shifted along to the next part, right? So we form B by shifting everything along. Now, for the little interval that confused a couple of people, which was the open interval that we got at the end, right? And I'll just clear all, it's probably easier. Yeah, cool. So the little open intervals here, they're the sections that we're dealing with, but we can think of them as kind of, I like to draw them like this, just because it uses the same kind of notation. But we're taking one section, so this is a section that's entirely in A, for example. One section here, and we include this number here, but we do not include this number here, because that number there will be in the next section that it attaches to, right? So if there is a number, say 1, if we took 1 here, 1 is in this set, this is 1. It can't be this number because it's inside the set, so it can't be right here, which means there must be another number over here which is larger than it. Or in other words, there is no maximal element in any of these intervals. So in particular, right at the end, when we have a 1, we must also have something larger than it. So we can't be partitioning 0, 1. We must be partitioning something larger than 0, 1, which is a contradiction because we've assumed that it was a partition of 0, 1. Cool.
Great.
Does anyone have any confusions on that question? I know that one's a little bit hard to wrap your head around. I don't blame anyone who kind of got lost. Yeah.
Also worth pointing out, we've left it out for brevity, but K is an integer. If you were writing a formal proof of it, you should be including that definition or that declaration.
Several of these proofs kind of assume that we're here to kind of explain what everything is. If you're writing these things out formally, you will need extra things. It's kind of hard to fit all of that formal stuff onto a slide. This is just giving you an idea of how you would approach the problem and the steps involved in getting to the solution, not necessarily all the details you would want to include. And I'm going to go fix those typos on the slide.
Okay, so this question's a bit tough. There's quite a lot going on in this question. So if we have a read of this question, what we're doing is we are trying to place 2017 integers in a circle. So we just place some integers, 2017 of them around a circle. And there's this condition where a configuration of integers is called arrangeable. Hang on, so a group of 5 integers is arrangeable if you can label them as A, B, C, D, and E in some order. So that if you do A minus B plus C minus D plus E is 29. So note that we can label the integers in any order we want. So for example, if A, B, C, if the numbers were 1, 2, 3, 4, 5, you could do 1 minus 2 plus 3 minus 4 plus 5, or 2 minus 3 plus 4 minus 5 plus 1. So you can choose what your A, B, C, D, and E are. So that's a condition for a group of 5 integers to be arrangeable. Now the question is, find all ways of find all 2017 tuples of integers around a circle and place them in clockwise order. And the condition is any 5 adjacent numbers have to be arrangeable. So arrangeable uses the definition at the top. So this is not an easy question. There's quite a lot going on. So the first thing that's notable is the number 29, which is equal to the sum. So it's a question of what's a k-tuple. So k-tuple is just a group of k integers. So for example, a 3-tuple could be 5, 6, 7, or 2, 7, 11. So 5-tuple could be 1, 4, 6, 10, 17.
Order matters though.
Oh yeah, and order matters, yeah. All right. So what you can see is 29 is quite an arbitrary number. So what you could conjecture is it doesn't really matter what number you put in place of 29. It could be 7, 11, it could be anything. And it turns out that the number on the right hand side, 29, it actually doesn't affect the problem that much. And another thing is, the annoying part of this problem is that the arrangeable 5-tuple of integers arrangeable, you can label the numbers in any way you want. So there's lots of ways in which 5 integers can be arrangeable. So it's hard to characterize what 5 tuples of integers are arrangeable. So it's not easy to immediately check whether 5 integers are arrangeable or not, because you have to go through a lot of cases, because for every labeling you have to check if the alternating sum and difference is 29. So that's the hard part of this problem. So what we could do is, since we have this 29 over here, we could try to transform all the integers so we have a nicer sum instead of 29. What it turns out is that this alternating sum and difference is very convenient, because if we subtract 29 from every number in the circle, if we just do it, what it turns out is that A will go down by 29, and negative B will go up by 29, C will go down by 29, negative D will go up by 29, and E will go down by 29. So the net change in A minus B plus C minus D plus E, the net change will be negative 29. So when you subtract 29 from every number, it turns out that a minus b plus c minus d plus e will be 29 minus 29, which is 0. So 0 is a lot nicer number than 29, so it's a lot easier to work with. So note that we are transforming this circle of numbers. So we're doing a transformation by subtracting 29 from every number. So now we could make a new definition of arrangeable. So instead of a minus b plus c minus d plus e equal to 29, we can now have a new definition of arrangeable where the alternating sum and difference has to be equal to 0. So now this turns out to be a lot easier to work with. Okay, so since we have a circle, we can consider 2 consecutive blocks of 5 numbers. So I might try to annotate if possible. I might draw a circle. So if you had numbers A, B, C, D, E, and F on adjacent positions in the circle. If you had 6 numbers in adjacent positions on the circle, you could consider this block of 5 over here, A, B, C, D, and E. And you can also consider the block of 5, B, C, D, E, and F. So you know that these have to be arrangeable. And since we've done the transformation, the alternating sum and difference will equal 0. But it's still haven't taken on the annoying part of the question, which is that you can choose, you can list, you can label numbers as anything you want. So to get rid of the annoying part, what we can try to do is try to see something that's common. Try to see something that's common for every possible way of labeling numbers. So this idea is called an invariant. So an invariant is something that holds true no matter what combination or situation you have. And it turns out in this problem, the invariant is the remainder when you divide this sum by 2, or this alternating sum and difference by 2. And you can see why it's an invariant because of so if you look at this alternating sum and difference, a minus b plus c minus d plus e, if we add 2b and add 2d, this means we're adding an even number to a minus b plus c minus d plus e, and we will get a plus b plus c plus d plus e. So what it means is, if we add an even number to this a minus b plus c minus d plus e, we will get the sum of the numbers. So what it means is, no matter how we label the numbers a, b, c, d, and e, this alternating sum and difference, the remainder of this alternating sum and difference when you divide by 2 will always be the same as the remainder when you divide a plus b plus c plus d plus e by 2. So note that no matter how you label the 5 numbers a, b, c, d, and e, the sum of them will always be the same. So that's our invariant. So invariant is, no matter how you label the 5 numbers a, b, c, d, and e, this alternating sum and difference, it will always be the same remainder when you divide by 2. And this remainder will be the same as the remainder when you divide the sum of the 5 numbers by 2. Okay, I'll redraw a diagram. Okay, let's use an eraser. Okay. So now we can apply what we've just shown to this circle of integers over here. So A, B, C, D, E, and F. So remember that our new definition of arrangeable is this alternating sum and difference being equal to 0. And from our invariant proof from earlier, it follows that the sum of the numbers A plus B plus C plus D plus E, this has to be even. So this is an even number. But now we can do the same thing with B, C, D, E, and F. So if we have 6 adjacent numbers on the circle, you can do the arrangeable thing for A, B, C, D, and E, and also for B, C, D, E, and F. And we get a similar statement of B plus C plus D plus E plus F being even. And now we can see that B plus C plus D plus E is common to both of the sums. So then it seems useful to subtract the first sum and the second sum, because lots of terms will cancel out. So if you do A plus B plus C plus D plus E and minus it by B plus C plus D plus E plus F, you will end up with A minus F. And remember that each of these numbers are even, so the difference will still be even. So it turns out that A and F, A minus F is even. So A minus F is even, which is the same as saying A and F leave the same remainder when you divide by 2. So A and F are both even or both odd. So that's what it says here in the slide. We see that for any Ni on the circle, if you look at Ni plus 5, which is 5 steps to the right of Ni and Ni plus 5 must leave the same remainder when you divide by 2. All right, yes. So we can, we can go to the next step. So another way of expressing it is Ni and Ni plus 5 have the same parity. All right, so go back to our circle. It means that if you take a position on the circle and then we go 5 steps clockwise, so we go 5 steps clockwise, this number will have the same parity. Okay. Oh yeah, so the question is, what's parity? So parity is, again, numbers, dividing numbers as either being odd or even. So if 2 numbers are both even, they have the same parity. If 2 numbers are both odd, they have the same parity. And if one number is even and another number is odd, they have different parity. Okay. So now what we can do is, we see that every number has the same parity as the number that is 5 steps clockwise of it. So we can keep on going around the circle and going up by 5 steps clockwise every time. And what we get is the first number, the 6th number, the 11th number, and so on until the 2016th number must have the same parity. But since the numbers are arrange clockwise in a circle. What it means is, if you have n 2016, so n 2016 over here, and clockwise of that is n 2017, and clockwise of that will be n1 again. So 2017 was the last number here, and if you go clockwise again, we'll go back to n1. And if we go if you go 5 steps clockwise of n 2016, we'll get to n4. So it means n4 has the same parity as all these numbers over here. And now we can start continuing the pattern with starting with n4. So note that numbers 1, 6, 11, and so on, they only cover the numbers that's 1 more than a multiple of 5. But we still have a lot of other positions to cover. So if we start at n4, we can cover the next batch of positions. So these are all the positions that are 4 more than multiple of 5. So 4, 9, and 14, so on. And eventually we can get that all this batch of positions again is the same parity as this batch of positions, and you can eventually get all 5 batches. So you can consider the positions that are 1 more than a multiple of 5, 2 more than a multiple of 5, and so on until 4 more than a multiple of 5 and exactly a multiple of 5. So if you keep on continuing the pattern, it turns out that every number ni has the same parity if you keep on continuing the process of going 5 steps clockwise. So another way of thinking of it is, if you start at a position on the circle and you keep on going 5 steps clockwise, eventually you'll hit every single position on the circle. And a reason why this is true is because 5 and 2017 have a greatest common divisor of 1. So if you replaced 5 and 2017 with any other numbers that have greatest common divisor of 1, this idea still holds. So if you go, for example, if you replace 2017 with 101 and 5 with 7, if you had a circle of 101 numbers and you start at a position and you go clockwise by 7 steps every time, eventually you'll hit all the positions. So again, this idea in general uses an idea called modular arithmetic, which is analyzing remainders, but it's a lot more general. So later workshops and sessions, we can cover modular arithmetic, but at the moment we don't need too much of it. All we need is to get that all the numbers have the same parity by keeping going clockwise by 5 steps every time. All right, so yeah, we can go to the next slide. Okay, so now we use a new idea, which is called infinite descent. So this is again a proof by contradiction idea. So what it states is, we can assume a configuration that works, that is minimal in some way. So let's say we have lots of configurations that satisfy a property. What we can do is assume that there is a minimum configuration that works, where you have to define the word minimum in a certain way. So it means out of all configurations that satisfy a property, you can choose the minimum of them. Oh yeah, I might have skipped a step. In fact, yeah, thanks for letting me know. All right. Yeah, so I accidentally skipped a step. So from earlier, so all the ni's have the same parity, but remember that the sum of adjacent 5 numbers has to be even from earlier. So we can do a mini contradiction proof within a contradiction proof. So if you assume that all the ni's are odd, then we're adding 5 odd numbers, which will still give us an odd number, but we know that the sum of these 5 numbers has to be even. So we get a mini contradiction. So what it turns out is that every number ni has to be even. Okay, so now we can go back to the idea of infinite descent. So in this question, what we can do is assume there's some solution. So in this example, the word solution means a configuration of 2017 numbers where adjacent 5 numbers satisfy the arrangement property, arrangeable property. So we assume there is a solution where the sum of the absolute values of every number is minimal and equal to S. So it means what's the smallest solution in some sense for the ni's. All right, so now I can go to the next slide. So remember that every number ni is even. Okay, so if we had 5 numbers A, B, C, D, and E, let's say these are arrangeable in some way. So we can randomly order them like this. So we can have D minus A plus B minus E plus C equals 0. Let's say we had a random way of ordering these 5 numbers, and this alternating sum and difference gives you 0. Now, let's say I divided every number by 2. So now A becomes A over 2, B becomes B over 2, and so on until E becomes E over 2. So now, if we divide every number by 2, and we still perform the same sum and difference for the corresponding numbers, we see that this sum will still equal 0. So if you just continue and dot dot dot, this new sum will equal 0. So it's because it's same as dividing D minus A plus B minus E plus C and dividing by 2. So what it says is that if you divide odd numbers by 2, the 5 adjacent numbers that were previously arrangeable will still be arrangeable after you divide all of them by 2. So what it means is you can say that if we divide every single number in the circle by 2, then we will get a new solution where every number is half of the corresponding number in the previous solution. So we can shrink the old solution to get a new solution. Okay, yeah, I can go next slide. Okay, so this is where our proof by contradiction comes in. So remember that S was, what we defined was the minimum possible sum for any solution, or minimum possible sum of absolute values for any solution. But now, remember from any solution, we can divide every number by 2 to get a new solution. So this new solution, the absolute value of every number will be divided by 2. So the sum of the absolute values in the new solution will be divided by 2. And again, this is problematic because the new sum is s over 2, but s over 2 is less than s in the case where s is more than 0. So again, we have reached a contradiction because s had to be the minimum sum, but if it's more than 0, we'll get an even smaller solution with sum s over 2. So we can say that this contradicts the minimality of the original solution. So it should be impossible to have a sum that is less than s, but somehow we've reached a sum that is less than s. So that's our contradiction. So what it means is that it's impossible for the sum of the absolute values of the numbers to be 0, to be more than 0. And since the absolute value of a number is at least 0, the only possible combination is where s is equal to 0 and every number is equal to 0. So it means in our modified sequence, we are forced to make all the numbers equal to 0. So we have no other choice to arrange the 2017 numbers. And now remember that we subtracted 29 from the original circle of numbers where we had a 29 here for the alternating sum and difference. But since we subtracted 29 at the start and we proved that all the subtracted numbers have to be 0, it means that in the original circle, all the numbers have to be 29. And we can check this works because if you have 5 adjacent numbers in the circle, if you do 29 minus 29 plus 29 minus 29 plus 29, you'll get 29 all the time. So if you have a circle with all 29s, this is a valid circle of integers. And using our proof by contradiction, we've shown that the only solution is when all the n's are 29. So that concludes the proof.
Great. Something you'll notice here is this question is asking you to find all the particular examples of 2017 tuples images. But we gave a proof by contradiction. So even though it was asking us to find something, we ended up showing something as a way of explaining that that's the only solution we can have. And in fact, coming up with that proof kind of led us towards what that 2017 tuple was going to be. So that's generally why competitions tend to be structured around proof arguments, because it restricts the kind of solutions people are going to give, and because it makes them explain their reasoning, explain their thought process. We only have a few minutes left. Are there any questions people have? Or is there anything people want to go back to and look at again? Cool. Yes, Siri, do you want to take that one?
Yeah, so the question is, does the problem generalize to any pair of odd tuples that are co-prime? Yeah, so the answer should be yes, because again, we subtracted the 29 at the start, and the 29 had no effect on the solution. So we subtracted 29 at the start, so problem is equivalent to finding numbers where the alternating sum and difference is 0. So the 29 has no effect on the question. So you could replace it with any integer. And for the tuples, okay, so remember in our proof, we relied on the fact that if we add 5 odd numbers together, the result is odd. So if you replace the 5 with any odd number, the sum of an odd number of odd numbers is still odd. So the same proof will work for 5 if you replace it with 7 or 9 and so on. But also, we use the fact that 2017 and 5 are co-prime. So if you remember, when you start at a point on the circle and go 5 steps clockwise all the time, we have to make sure we can reach every single point on the circle. So that requires the 5 and the 2017 to be co-prime. And so if you replace with any co-prime, if you replace 5 and 2017 with any co-prime numbers where 5 is also odd, yeah, the problem will hold. So that's a generalization of the problem.
That's also something you can kind of see in questions like this. It's not exactly clear what facts you're going to be using and where to go with the question, but you can look at the numbers in the question and kind of how it's designed, right? So you have a bunch of numbers where you take the alternating sum as a certain number, and you're looking for a bunch of other numbers where you're taking kind of consecutive numbers, adding them in a certain way to get a certain number. This kind of reeks of number theory, right? So even looking at the question, you can start to notice certain things, like 5 is co-prime to 2017. Maybe that has something to do with it. And it's a circle of 2017. We're taking 5s, they're co-prime, so we know we can, if one property is satisfied amongst every 5th one, then we're kind of good to go, right? If you do enough questions like this, you'll kind of start to see number theoretic questions have certain properties, maybe something more analysis-y. You can look at it and go, what kind of properties can I pull out of this that I might be able to use in an argument later on? And even if you don't know where they come up, just having them available and like well-defined, so you can look at that and go, I can use that now, makes your proof kind of much easier. It flows out of you easier. You know your options rather than having to, at every step, explore your options, right?
Wonderful. I think another thing I would observe is if this question were pulled from a competition, I would guess that the competition was from 2017. Usually it's good to know the prime factorization of the competition year, because sometimes they like to include that in questions.